So we got a few interesting integration problems here. First one is the integral of cos of root x dx. And the way to do this one is to say let u equals root x. That's the substitution that you should make to try to integrate this function. And from here, we can say that du equals 1 divided by 2 root x dx. And from this, we can insert this into our integral here to get this function that's in terms of x in terms of u. So this will be equal to the integral of the cosine of u, and then dx is going to be equal to 2 root x du times 2 root x du. But of course, u equals root x, so we can substitute that into our integral here. If we bring the 2 out front, we're going to get 2 times the integral of u cos u du. And then from here, this is a fairly standard integration by parts problem. So it's a bit confusing here with the u variable. Our u is going to be equal to u. That's the one I would make, because then when you differentiate this, you're going to get 1. So u prime will be equal to 1. Our v prime will then be cos u, which is easy to integrate. So the integral of this, of cosine, gives us sine. So v is going to be equal to sine u. So now if we use our parts trick, bring it 2 times uv, which is going to be u sine u, minus the integral of u prime v, which is the integral of sine u du. So we can expand our 2 out. We're going to get 2u sine u minus 2 times the integral of sine, which is plus 2 times the integral of negative sine. And of course, if we differentiate cos, we get negative sine. So this is going to be equal to positive 2 cos u plus c. And now if we just return our substitution, our final answer is going to be 2 root x sine root x plus 2 cos root x plus c. So our first integration problem is done. Now this next one here is also kind of interesting. And when I look at this one, I notice in the bottom here that there is this 1 plus x4. And this is really similar, or it is the form a squared plus x squared. And whenever you have this in the denominator, a good substitution that you can try making is let x equal tan theta, or a tan theta. So in this case, I'm going to say let x squared equal tan theta. Our a value is just 1, so we're just going to make this substitution here. So now if we differentiate this, we're going to get 2x dx equals secant squared theta d theta. So we can substitute this in. So this is going to be the integral of 2x over top of 1 plus tan squared theta. And then dx is going to be secant squared theta d theta divided by 2x. And obviously these cross out, and we know that 1 plus tan squared theta equals secant squared theta. So these will also cancel out. And we're just left with the integral of d theta, which is equal to theta plus c. And since tan theta equals x squared, then theta is going to be equal to arctan of x squared plus c. So that's the final answer for that integral there. Now this last one here is quite a bit more tricky than the other ones. And the trick to this one is to use the substitution u equals tan of x over 2. That's called a Weierstrass substitution. So if we use this little trick here, let's say we were to draw a right triangle. This is the right angle here. Our angle is going to be x over 2. And we know that tan of x over 2 is u. So it's going to be u1, and this will be 1 plus u squared. Now, from this, we can see right away that sine of x over 2 is going to be opposite over hypotenuse. So it's going to be u over square root of 1 plus u squared. U over top square root of 1 plus u squared. And we also see that cos of x over 2 is going to be adjacent over hypotenuse, 1 over root of 1 plus u squared. So we're going to get this equation here. And now we also know the following identity. We know that sine 2x equals 2 sine x cos x. So therefore, if we substitute x over 2 in place of x, we're going to find the following, that sine of x is going to be equal to 2 sine of x over 2 cos of x over 2. And using this for sine x, we can substitute what we know in terms of u in for our integral here. So therefore, sine x is going to be equal to 2 times u over the square root of 1 plus u squared times the square root, or times 1 over the square root of 1 plus u squared. And so using this, we can just expand. So we're going to find that sine x is equal to 2u over 1 plus u squared. So we can substitute this into our integral to get it from being in terms of x to be in terms of u. So the integral of 1 over 1 plus sine x dx now becomes the integral of 1 over 1 plus 2u over 1 plus u squared. And then we know that u equals tan of x over 2, so du equals 1 over 2 secant squared x over 2 dx. So now if we substitute for dx, we're going to find that dx is equal to 2 cos squared x over 2 du. Or du. So we get that there. So now if we know that cos of x over 2 is equal to 1 over square root of 1 plus u squared. So if we just square that, we're going to find the following. This would be equal to the integral of 2 times 1 over 1 plus u squared over top of, now if we were to get a common denominator here on the bottom, we're going to get 1 plus u squared plus 2u over top of 1 plus u squared. So, and then times du. So now we can just write this as a single fraction. This will be equal to the integral of 2 over 1 plus u squared times, or rather it's going to be 2 times 1 plus u squared divided by 1 plus u squared times 1 plus u squared plus 2u. That's what we're going to get on the bottom. And now we can cross out the 1 plus u squared here. And so what we're left with now is going to be equal to the integral of 2 over u squared plus 2u plus 1 du. Now if we put this into factored form, we're looking for what multiplies to 1 and adds to 2, which would be 1 and 1. So if we factor this, it's going to be 2 over u plus 1 squared du. And this can be easily integrated. This is going to be equal to negative 2 over u plus 1 plus c. Now the integration is complete. We just have to return u back in terms of x. But we know that up top here, we said u equals tan of x over 2. So we just return that in, and this is equal to negative 2 over tan x over 2 plus 1 plus c.